All right, our goal for this video is to graph in standard form and then be able to identify key features. I used to do standard and factored together, and I moved factored into vertex form. So today is just standard form, which is it's right down here. No reason to rewrite it. Okay, so standard form, that's the ax squared plus bx plus c. Note that there is a little note there, a cannot equal 0, because otherwise we would not have a quadratic function. So you have to have a value for a. If a is positive, it opens up the parabola. If it's negative, it opens down. The bigger the a is, the more narrow it is. Remember, that is a vertical stretch. And then the smaller a is between 0 and 1, it should say, the wider it is, and that is a vertical shrink. Okay, in standard form, we can find the axis of symmetry using the equation x equals negative b over 2a. So that's using the a, b, and c from the standard form equation. So you take the opposite of b and you divide it by twice the value of a, essentially. And then that gives us our axis of symmetry. And then since our axis of symmetry, our vertex lies on that axis of symmetry somewhere, the x coordinate of the vertex has the same value of negative b over 2a. To find the y value, you plug in the x that you get. And then standard form also gives us the y-intercept, because the y-intercept lies on the y-axis. That's wherever the x value is equal to 0. So if you think about plugging in 0 into the standard equation, you would a times 0 squared plus b times 0 plus c, you would get c. So your y-intercept is always your constant value at the end of the equation. All right, so we can tell which way this parabola opens by looking at the a value, the constant out front. So that's negative 2. So a equals negative 2. Since it's negative, this parabola will open down. Then we can find the axis of symmetry. This is our a, our b is negative 4, and our c is negative 3. By using that equation, negative b over 2a, or the opposite of b over twice the value of a. So in this case, it would be negative 4 over 2 times negative 2. So it ends up being positive 4. So the opposite of b over 2 times a, which would be negative 4. 4 divided by negative 4 is negative 1. So my axis of symmetry is going to be the vertical line, x equals negative 1. The axis of symmetry does need to be written as an equation because it represents this vertical line that crosses through all the negative 1 values of x. Then the vertex lies somewhere on that axis of symmetry. So we're going to graph the x coordinate of the vertex. We're going to plug in negative 1 for the x coordinate of the vertex. So plug that back into the equation for x. So it was negative 2, and then it was x squared, so it'll be negative 1 squared, minus 4 times negative 1, minus 3. So if you're using a calculator to do this, make sure that you're putting the negative value in parentheses, exponents on the outside of parentheses, etc. Because negative 1 squared is 1, times negative 2 would be negative 2. And then negative 4 times negative 1 would be positive 4. And then minus 3. So I'd get 2 minus 3. I'm ending up with negative 1. So graphing my vertex at negative 1, negative 1. I do have a y-intercept. If I plugged in 0 for x, my y-intercept would be negative 3, my c value. So the c value is the y-intercept. So I can plug that or graph that now, and I could reflect it over, and then I have 2 points to make the parabola, but it's not going to be a super accurate graph if I only graph 2 points. So I'm going to graph a couple more using the parent function like we did with vertex in standard or factored form. So I'm going to think about my parent function table is going to be 0, 1, 2, 3. And then my y values are just those x's squared. So 0, 1, 4, 9. Then this A value is negative 2. So you're going to take the middle column times negative 2. So multiplying all the middle ones by negative 2. And then I graph that table from my vertex. So the A value doesn't move the function at all. So 0, 0 is still at the vertex point, which in this case is negative 1, negative 1. And then 1 down 2. So over 1 down 2, that's my y-intercept. I already had that graphed. Then over 2 down 8. So over 2 down 8. Make sure you're going from the vertex. So over 2 and then 1, 2, 3, 4, 5, 6, 7, 8. And then reflect that over. So 2 away from the axis of symmetry, so 2 away. Now over 3 down 18 is going to be off my graph, so no need to graph that one. But at least I had 2 more points to make it a little bit more accurate. This graph is more narrow than the parent function because the A value is 2, so it's dropping faster. And so we would say that there's a vertical stretch here. There's also a reflection over the x-axis because it's opening down. And then it's been shifted to the left one and down one as well. The vertex is a maximum point because it opens down. That maximum is at y equals negative 1. That's the highest y value. Similar to the domain of the other forms, quadratic equations have no restrictions to what you can plug in. You can square any real number essentially. So x is an element of the real numbers for domain, and the output values represent our range values or our y values. And if we look at our picture, we can see that, you know, the maximum y value is at negative 1, and then everything else, all my other output values, were below that. So y less than or equal to negative 1 is my range. All right. So here we have y equals negative 1/2 x squared minus x plus 1. So our A value in this example is negative 1/2, and it opens down then because it's negative. The axis of symmetry, we're going to use that equation where it's the negative b over 2a. So in this example, a is negative 1/2, b is negative 1 because we have a negative x, and then c is 1. So we're going to have x equals negative 1 over 2 times negative 1/2. So negative 1 is going to be positive 1, and then 2 times negative 1/2 will be negative 1. 1 divided by negative 1 will be negative 1. So x equals negative 1 is our axis of symmetry. So we have the same axis of symmetry as our last example. It needs to be written as an equation of a line. Then we find our vertex by plugging that negative 1 in for the x coordinate back into the equation. So y equals, it'll be negative 1/2 times negative 1 squared minus 1 times negative 1 plus 1. So negative 1 squared is positive 1 times negative 1/2 will be negative 0.5 or negative 1/2. Then we have negative 1 times negative 1, which is positive 1, and then plus 1 again. Negative 1/2 plus 1 will be positive 1/2 plus 1 will be 1.5. So if you're using a calculator, make sure you're plugging that in carefully. So our vertex is at negative 1 and 1.5. Or in fraction form, it would be 3/2. Typically with graphing, I use decimals because they're easier to graph. But of course, if your vertex ended up being at like 1/3, it would be more accurate to write 1/3 than it would be to write 0.3. The y-intercept in this case is our c value, which would be 1. So our y-intercept would be at the value 0, 1. And you could reflect that over. But that really doesn't give me very much to work with there. So I'm going to graph a couple more points using my parent function table. So 0, 1, 2, 3, 0, 1, 4, 9 stays the same every time. Then the A value is negative 1/2. So you're going to take half of the middle, negative 1/2 times the middle column. So 0, negative 0.5, -2, and -4.5. Then graph the first and last column. So 0, 0 is my vertex. Over 1, down a half, I have graphed already. And then over 2, and then down 2. So over 2, and then down 2. We have to be a little careful because it's going by, we're essentially going by halves here, but then over 3, and then down 1, 2, 3, 4.5. And then reflecting that over very carefully. And then that gives me enough points to graph. So I just had to be really careful with the 0.5s there. So this graph is going to be wider, which means we have a vertical shrink here. It has a maximum value again because it opens down. That maximum value is happening at the y value 1.5. The domain is all real numbers, and all my y values are less than or equal to 1.5. Do one more in standard form. Okay, this one opens down again. A is equal to -1. I don't know why all my examples open down, I guess. Axis of symmetry. In this one, if you notice, I have 0 x's. So that means that my b value is 0. So when I find my axis of symmetry, it's going to be -0 over 2 times -1. Well, -0 is just 0, and 0 divided by anything is 0. So my axis of symmetry is going to be the y-axis, where x equals 0. Plugging that back in to the vertex, to get the vertex, it's going to plug into y equals negative, and then 0 squared minus 2. -0 squared is 0, minus 2 is -2. So my vertex is at 0, -2. My y-intercept is the c value, which again is 0, -2. So in this one, my vertex and my y-intercept are the same. So I'm going to graph this. So I need a couple more points. I'm going to come back to the roots here in a second. So 0, 1, 4, 9, 0, 1, sorry, I started the wrong. 0, 1, 2, 3, then 0, 1, 4, 9. And then A was -1. Oh gosh, it's getting late. Okay, -1 times y. So 0, -1, -4, -9. So I can graph this starting at my vertex, over 1, down 1, then over 2, down 4, then over 2 down, or over 3, down 9, which is just off my graph, but I'll throw it on there. All right. Okay, so I had asked for the roots in this one. Now, typically the roots are your x-intercepts. So remember, we have 3 names for x-intercepts: roots, solutions, x-intercepts, or we can call them zeros. So 4 names. And we call them x-intercepts because it's where it crosses the x-axis. Now, if they doesn't cross the x-axis, that means that our solutions are not real. So we don't have any rational x-intercepts answers. That doesn't mean they don't exist. That just means they are going to be complex. So that's why we also call x-intercepts solutions or roots. So we're going to have some complex roots. We also call them zeros because it is where it makes the equation equal 0. So if we take -x squared minus 2 and we set it equal to 0 for y, so 0 equals x squared minus 2, or -x squared minus 2, or maybe it would be better if you did -x squared minus 2 equals 0. So set your equation equal to 0 instead of y, and then solve for x. So I'm going to add 2 to both sides, and I'm going to get -x squared equals 2. Then divide by -1, and I'm going to get x squared equals -2. Take the square root of both sides, and I'm going to get x equals, I ran out of room, plus or minus, you're going to have 2 roots. They come in pairs. And then the square root of negative 2 is going to be I square roots of 2. So our roots are positive I square roots of 2 and negative I square roots of 2. And you could do x equals those. So those are your two answers, or your solutions, or your zeros. Those values would make the equation equal 0. And I knew that they were going to be imaginary again because I didn't have any x-intercepts. So typically roots means x-intercepts, or solutions where it crosses the x-axis. If it doesn't cross the x-axis, then those are complex roots, and you have to solve for them. This parabola has a maximum value because it opens down. The maximum value is at -2. The domain is all real numbers. All my y values are less than or equal to -2. Had this parabola opened up instead, your output values would have been greater than or equal to -2. So I apologize for not doing an example like that. Okay, thanks for watching.